Thank you for that great introduction. It's a great pleasure to be here, an honor to be here. As Catherine mentioned, very special because Catherine was a friend and colleague of my father's many years ago when I was growing up. And at the time, both my dad and Catherine were working for the Singer Corporation. Not all of my dad's colleagues were really all that interesting or exciting, if you can imagine what a typical 70s corporate manager was like. And Catherine was not that way. And very much the sort of early role model for me as what an exciting person can do in the business world and how you can stay creative and interesting, even if you happen to be working at Singer, which wasn't always the most exciting and interesting place. It's a pleasure to be here again. Actually, hearing Jim's talk and some of the early conversations I had beforehand made me think I should have said more about one of my earlier books, which was about the history of human-machine relationships in the 20s, 30s, and 40s, and had a lot to do with New Jersey, both Fort Monmouth and RCA, and particularly Bell Labs. So I'm fully on board with the understanding of the early role as human-machine valley, as it were, for New Jersey. Today I'm going to talk to you about an idea from my most recent book called Situated Autonomy, a little bit of the analysis from the book, and then a little bit where I think we may be going moving forward. And I'm going to go back a little bit further than Jim did, almost 50 years to the moon landings. This is actually my friend and colleague Dave Scott standing in front of the lunar module on Apollo 16. And the lunar module was what today we might call an autonomous robot, or possibly a semi-autonomous robot. It had the capability of landing fully autonomously with no human intervention. And the computers and the software for this machine were actually built at MIT. Back to the semiconductor story, it was the first integrated circuit computer, the first computer and software system that people staked their lives on. And yes, it only had 32K of memory, but how many of you would risk your life on the computer on your desktop working flawlessly without a hitch for 2 weeks straight? And nobody ever raises their hand in response to that question. That's exactly what the Apollo guidance computer did. It did so 6 and more times. But interestingly enough, when the engineers at MIT first got the assignment to build this computer, they were convinced they could build a computer to land on the moon, no problem. And NASA came and said, all right, what should the interface be? And the answer came from MIT engineers, well, interface, it really only needs 2 buttons. One button says, take me to the moon, and one button says, take me home. Why would it need more than that? It turned out it needed a great deal more than that. And what ended up being produced was actually the first digital fly-by-wire system, technology that is now in virtually every airliner, certainly in the one that I flew. Actually, I flew on a 737 down here. It's not digital fly-by-wire, but most of them are. And a very, very rich, complicated human interface. And this was the subject of a book that I wrote in 2008 called Digital Apollo, where very many of these same issues that we're talking about today came up in the context of the lunar landing. What are the people there for? Who do we need? What is the impact on training? What is the impact on our own sense of ourselves? These were old debates, actually, in labor relations and technologies and factory floors, given a new dimension by the computers and the new technology of moon landing, much as they're being given new dimensions today. The image on the right, which is actually just the cover of the book blown up a little bit, is an image, it's actually made for me by John Knoll, who's the head animator for Industrial Light and Magic, who did all the animations for the Apollo 13 movie. And it's what the view looked like out the window if you were Neil Armstrong about 200 feet above the moon on Apollo 11 when he turned off the automatic targeting system and landed with his hand on the stick. Very, very interesting moment. Why he did that, I won't go into it too much today, other than to say the last 200 pages are all about the last 10 minutes of the landing. And then on the following 5 landings, every single commander of an Apollo mission did exactly the same thing as Neil did. My more recent book came out about a year ago, called Our Robots Ourselves, talks about the myths of autonomy, sort of building on this Apollo experience. And the idea is that by looking at extreme environments, I come out of both studying spaceflight and working in deep ocean robotics for many years, we can glimpse a little bit about the future. There, people have been using robotics, autonomous systems, remote controlled systems for decades. Similarly in aviation, similarly in remote warfare. And those are some of the dynamics that we're just beginning to see in our factories, in our homes, potentially in our cities. One of the stories that one comes up with is that Apollo story gets repeated over and over and over again. We think this vehicle is going to be autonomous, but to actually make it work in a real setting, it ends up having to be situated within a human environment in one way or another. There's a whole chapter on the Predator, the US Air Force's drone, which you've heard a lot about in Iraq and Afghanistan. Same exact story, shifted by 30 years. The engineer said, oh, what do we need an interface for? It's an unmanned aircraft. That's the early 90s. By the early 2000s, the Predator is being very actively used, very important, very unusual new weapon being used in Iraq and Afghanistan and other theaters of war. The Air Force is forced to ban the term unmanned because it takes hundreds of people to operate the Predator, distributed all over the world. So the way that these robotic systems end up coming into use and becoming useful is different than we expected. As Dibner pointed out, the future looks different than we expect. And when robotic systems become successful, it's often because, in the case of the Predator, very painfully and very expensively, but still nonetheless it happened, they become situated into human work, in human organizations, often in interesting and surprising ways. And so this book really draws on aviation, spaceflight, undersea exploration, and warfare as extreme environments where we can learn something of what's happening in the future. Here's one example from the book. I spent my early career and many of the last 25 years working in the deep ocean out of the Oceanographic Institution in Woods Hole. I worked for the group that found the Titanic and the Bismarck. This is a kind of family tree of vehicles from the early 2000s and reflects the kind of way that we expected the technology to evolve. There's a manned vehicle here called Alvin that explored the Titanic in 1986. Actually, Alvin's been diving since 1964. Some of the early remotely controlled vehicles, ones I worked on in the 80s and 90s, Jason and Jason 2. And then these autonomous vehicles that, when we first started designing them, figured they would be autonomous. Send them off the ship, they go do the science for you, they come back, they tell you what happens. And we actually thought then that there was this natural progression from manned to remote to autonomous. And that's all, you see that very much in the kind of conversation about automobiles today. But what's interesting is actually that's not what happened. Indeed, we do have sort of autonomous vehicles today in that they're tetherless, they don't have cables connecting them. But the manned vehicles are all still there. Alvin is actually, they've built a new version of it, it's still coming out. And if anything, the lines between what's manned and what's autonomous and what's remotely controlled are blurring. So we don't have nearly that clear sense of these different categories as they did with the Apollo landing. Actually talk a little bit on, how is an airliner today not a telerobot that you sit in? It really is very much that way. And most of these systems are kind of blurring. Indeed, if we look just at one example from deep ocean exploration, again, we have the autonomous vehicle here that when we first started building, we figured we'd send them off and we wouldn't see them again for days and days later. But actually, that's not how they end up working out at all. They have acoustic communication, sort of like old 1990s modems that send data back and forth. We can send kind of basic text messages to them. We talk to them as much as we can during the course of their operations, much as no driverless car is ever going to work very well without linkages to a 4G or a 5G network. That's very much part of that story. They're not autonomous at all. Then lo and behold, actually I was one of the first people to call attention to this, is like every autonomous vehicle that we ever operate is a hybrid manned vehicle or autonomous vehicle, because a ship is a manned vehicle, and we still operate oceanographic ships, and we still send these autonomous vehicles off the ship and then come back. So it's this constant kind of give and take of autonomous human control, autonomous human control. In fact, the book opens with a scene from one of these vehicles operated by colleagues of mine finding the wreckage of the Air France 447, terrible tragic crash in the Atlantic under very, very similar operational settings. And what we're finding again is all kinds of interesting, weird hybrids of human, remote, and autonomous. And many of those hybrids get mixed and matched as we achieve this kind of situated autonomy that's within a human setting. As we look into the economic and business world, I'll come to that. Economics and business are by definition human settings, places where things are valuable to people. The rest of the book goes through, I mentioned Predator, there's a chapter on the repair of the Hubble Space Telescope, chapter on the Mars exploration rovers, chapter on heads-up displays in aircraft cockpits and all the different kinds of automation you find in aircraft cockpits, and again, the undersea chapter. All of these are extreme environments that have been operating these kinds of robotics for decades and have learned some lessons that are valuable for us going forward as we think about things like autonomous cars and other types of new kinds of automation. So that's a bit of the historian in me, most of how I've made my academic career. I'm also an engineer, and I like to build stuff, and I really put the challenge to myself for the next phase of my career. If we believe in situated autonomy, if we believe in these kind of interesting hybrids, how can we build a world, and how can we build technology that enables much more fluid mixes between people and machines? And so I founded this company called Humatics, which I'll tell you about in a minute, but I wanted to read, Catherine asked about the Kinsey study that she very thoughtfully sent out, which is really the perfect kind of header reading for today's topic. There's a section in there that really captures my whole thesis and everything that we're trying to do beautifully well, so I'll read it from page 18. Workers will need to work more closely with technology, freeing up more time to focus on intrinsically human capabilities that machines cannot yet match. Men and women in the workplace will need to engage more comprehensively with machines as part of their everyday activities. Tighter integration with technology will free up time for human workers, including managers, to focus more fully on activities to which they bring skills that machines have yet to master. So if you take that conclusion, which comes, I actually haven't read the full research report behind the synopsis, but I will, and I think it's quite rich, and very well researched, as McKinsey's work tends to be. What do we mean by that, and how do we invent our way forward that way, toward a world of collaborative humans and machines, rather than machines replacing people? So we put this company together, and I won't fill you in with all the details of our board, other than to say our two founding scientific advisors are Dave Scott, who helped design the Apollo guidance computer and then actually piloted the lunar module to land on the moon in Apollo 15, and Bob Ballard, who was my mentor in the undersea world, who you may be familiar with as the discoverer of the Titanic. So we're bringing a lot of these same extreme environment learning into these more everyday and future-oriented arenas. Now, let me go back and tell the same story a little bit slightly differently than I just told you. If you Google robot image search, I did this yesterday, this is what you get, okay? That's a decent kind of stand-in for what the cultural image of a robot is. And I would say both of this, and the image I'll show you in a minute, kind of capture what many of my AI and robotics colleagues think about, and what many in the public think about too, as a robot. It's sort of like a person. It moves around in ways that are like people. You'll notice all of these pictures, I think every single one of them doesn't have anything around the robot, right? It's totally by itself. There's no environment at all to the robot. Ditto, by the way, about how driverless cars see the world. This is an image, pretty typical one of a LiDAR-based image that a driverless car has. And it's me, looking out into the world, and everything I know about the world only comes from the reflection of my energy, my kind of great ego, sending energy out and looking for reflection back. Again, this image of how a driverless car sees the world, which is very much Google's driverless car philosophy from about 2015. They've modified it, I think, since then. No relationship to anything around it, very little relationship to the people around it, and no sense of living in any kind of human environment. And yet, I've been fond of saying, the human-built environment is the greatest AI we know. Right? There is so much intelligence built into the environment. We as people are very good at fluidly drawing that intelligence, whether it's where the door is or the exit sign or the nature of the space. This view is very much, I mean, and it makes sense to me because I teach adolescent engineers at MIT, and this is how they see the world, right? And we teach them to see the world this way. It's all about you. You have no relationship to anybody else, and if you are just willful enough and smart enough, you're going to get there on your own. But of course, I can tell by the knowing laughs, we all know that's not quite how the world works. Now, this image is actually from an Amazon fulfillment center. And I'm sure you may be familiar with the Kiva robots that Amazon bought a company called Kiva, a Massachusetts-based company, started by a couple of colleagues of mine. It's just I Googled Amazon Kiva robot. And found this image. It's quite simplified compared to what you actually see in a fulfillment center. But you see there's a person, okay? And there's two robots you see there, and there's all this structure around them, whether it's the shelving structure, and there's products, okay? And to me, this set of relationships between people, robots, and infrastructure is actually much more the picture we want to have rather than the picture of the robot by itself, all on its own in the future. It has very, very profound implications. A couple pieces of this, okay? Everybody at Kiva, and I know them well, if this is the robot, it looks like a lawnmower, maybe like even a kind of debased lawnmower. The robot part of this system is a trivial part of it. It's basically a little thing that moves around and picks up shelves. But it's under software control. There are hundreds of these things in every one of these automated warehouses. And the actual robot is just the thing that moves around. It doesn't have a gripper on it, it doesn't have an arm, it doesn't look like a person, it doesn't have eyebrows and eyelashes and ears and all that cute stuff. And nobody would say that the robot there is the key thing about what makes that system important. What makes that system important is the coordination of hundreds of those robots, the software system that integrates them all, that optimizes the flow of the materials through the system, the way that they, just as the McKinsey report says, keep the people in the loop to do things that people are good at, combination of recognition and grasping and other manipulation things. And it's this kind of hybrid thing. Now, interestingly enough, when I showed this picture to Dave Scott, who is now in his early 80s, again, who landed on the moon, the most sophisticated technology operator of his day, he said, it's real exciting what you guys are doing at Humatics, Dave, I get it, but where's the robot? Okay? And I had a moment when he said that to me because I realized I was taking something for granted based on my work that I wasn't making clear enough, which is that in this case, it's the entire fulfillment center that's the robot. And there are little things that move around, and there's software, and there are people, and it's the sum total of those things that's the robot. That's the picture we want to think about moving forward. So as we ask, where are the people, where are the machines, who's taking whose jobs, we want to look at it with at least that size of system. And I can tell you right now that Amazon doesn't stop seeing the fulfillment center as the robot. For them, it's the entire supply chain is the robot. In fact, when you sit down at your web browser and you click to buy your shaving cream or whatnot on Amazon, you are the operator of that robot, operating that supply chain. So this gives us a new way to think about how all these different elements can relate to each other. And I keep looking in different places and keep coming up against these three key elements: people, robots, and infrastructure. You could call it people, places, and things. That's a slightly more accessible way to put it. And what my company is doing now is inventing technologies that improve the relationships between these three elements. And again, I added some labels here. There's a lot of different ways you can think about these different pieces. Not all robots, again, look like R2-D2 or C-3PO. In fact, almost none of them do. They may be mobile platforms. They may be lunar landers. They may be Airbus airliners. Same thing, there are a lot of different kinds of people. Some people, and each of you is probably three of these kinds of people in the course of the day. When you sit behind the wheel of your car, you are an operator. When you're in a CVS, you're a consumer. When you're at home, you're a different kind of person. So there are many, many different hats that people wear. And same thing with infrastructure. Okay, and one of the reasons that I'm so interested in what's going on in both factories and in distribution centers these days, I think that's where we're glimpsing the future now. And if we think about what our cities are going to look like, maybe our homes, I'm a little less clear on what our homes might look like, but certainly cities, we're going to see that same set of relationships emerging: people, robots, and infrastructure. How do those things relate to each other? I often say nobody knows what's going to happen with driverless cars, and I don't profess to know, but what I will guarantee you is going to happen in parallel with the Internet of Things. There is no way that driverless cars are going to be on their own in these environments. They're already not. So we developed a set of technologies actually based on stuff that I did undersea that we're calling MicroLocation. And it's basically, think about a little GPS network between you and whatever it is you're interacting with, whether it's a robot or infrastructure, and bringing a new level of digital precision to that interaction. Right now, one of the big sticking points out in many of these environments is we don't know where anything is. GPS has revolutionized our ability to know where things are in a kind of macro scale on the surface of the globe. It doesn't work at all indoors. It doesn't work super well in cities. It doesn't work in subways. Lots of environments where economic value is created, GPS doesn't work. And we're beginning to think about not only how can we locate things indoors, but how can we locate them with incredibly high levels of precision. And what does that precision buy you? Now to return, I'll spend most of the rest of the talk talking about industrial automation in factories. Now we have the possibility of technologies that will allow people and robots to see each other with a great deal of precision, much more precision than we're able to get today with cameras and vision systems, and locate each other so they can work collaboratively alongside each other. Here's one image of that from an automotive plant. Another one, in this case, there aren't necessarily robots, again, in the traditional sense, but everybody's part of the robot. And we can understand where the workers' bodies are with a great deal of precision, which makes the work both safer and more efficient, but also gives a whole new level of insight into how we can improve and use human motion in the ways that people can really add value to these things. You can do some of this in a Hollywood studio today. You can take a room this size and add $1 million worth of cameras to it and cover up all the windows and cover up your hair and your watch, and you can track people. They do that for Hollywood productions, but not in a way that's suitable for the factory floor. We're actually just about to introduce this as a pilot system. It'll probably be out next year as an actual product where you can hang a kind of unit on the wall that's about the size of this exit sign over in the corner, and then you have these little beacons that you can put on all these different things and localize them to within millimeters, many hundreds of times per second, whether it's putting them, again, on people, on robots, or on the infrastructure itself. And use that data then, it's as much about data as it is about hardware, to link the digital world together between, again, these three key elements. There's a whole software ecosystem that gets built around it. If you are operating a factory and all labor organizations know that they have workers who are more productive than other workers, that's usually pretty easy to measure from the output. The big question is why. And if you can bring the average worker up to even a few percentage points on average up to where the level of the average worker is closer to the level of the best worker, you have huge productivity gains there. We're actually finding that a lot of our early customers are many places, by the way, where there are high value, relatively low volume products, where it's actually not cost effective to automate them for any time in the foreseeable future. Yet they're under huge pressure to increase production rates and increase efficiency with the human workers they have. Here's one data set that we collected, which is actually really cool. This is a piano player, and you're looking down, in this case, on a keyboard. In this case, you're looking forward into the keyboard, and the cloud of motion that you get from a piano player. And we took a dozen piano players. They all played exactly the same piece. It was all data was synchronized to the music they were playing, and they were actually all professionals. Looking at the data, even without fancy machine learning stuff, just by eyeball, you could see great differences in the data. And it turned out that some of the players, I don't have comparative data here, had a lot more motion than the other players. And our first instinct was like, those are the less expert players. And it turned out to be exactly the opposite. The inexpert players, who were professionals but sort of barroom level players from Boston area, tended to play in fairly rigid, their wrists were in very kind of rigid lines. And actually this data set is from a professor of piano performance at the New England Conservatory, very much the high end of the professionals, which is correlated to what their hourly rate was when we paid them for this. Much more kind of vertical motion you can see there. We interviewed her after, and it's not because of the artistic flourish of the performance, is because actually the greater motion is a more effective, efficient use of the dynamics of the human body in this case. The more rigid motion is actually more straining and stiffer and less efficient. And we're actually beginning, this is looking down on a worker doing a fulfillment center task, pulling products out of bins, and with some of the tracking overlaid there, we're already able to see differences in skill level and differences in performance. So you couple this kind of system with a kind of real-time feedback system, and you begin to glimpse at least one version of what we imagine the future of work. All the cool technology, all the great AI, virtual augmented reality, but done to amplify the worker and to let the people do what they're best at, let the machines do what they're best at. And I think the world is our oyster as far as what we're going to learn about where that goes. Very, very concrete tasks. These are going into pilots this summer. Simple safety tasks, safety operations, where we're able to define with incredible precision now different levels of safety, and bringing the people into the closer, more intimate proximity with machines. Jim showed you the picture before of the automobile production line with no people in it. That's actually the reason there are no people there is a limitation of the robots themselves, which is they don't know how to work around people, right? That human-less line is going to look as obsolete as the 1950s Ford factory line looks, we believe. We want to be very much in a mode where the people are working in intimate collaboration with people, and actually all of our technology is moving down to the chip level where it'll be embedded in all these different robots all the time, and both the people and the robots are in very, very close proximity to each other, and they can actually really begin to work together rather than now it's basically a relationship of fear on the factory floor.
Is he in charge or is the robot in charge?
That's a good question. Okay. Are you in charge when you order from Amazon, or is Amazon in charge?
I'm an investor in robot companies, so I really care about that.
The earliest use cases that we're developing are actually, the simplest ones are the robot stays away but in a more intimate proximity. And the basic model for all of them is the human takes the lead. The robot either hands a tool or says, if you're working on this part of the line, I'm going to go over here and work on that part of the line till you're done, then I come over there. Those are still kind of complex avoidance strategies, but we're really hoping to get into much more intimate, true collaboration strategies. Again, you've heard, I'm sure, of collaborative robotics, very interesting, important new industry rising up, but they're very small robots, A, and B, the only thing that makes them collaborative is they won't cut your head off. It's an important, difficult step to get to, but we got to get further on. And all the big robots don't have those features built in. We need to do better there. So, coming out of the aerospace world, you need 3 nines after your 99 point of reliability in order to make things safety critical. We want to have chips in every single bicycle. Just those little flashing LED lights, right? They're lovely for human operators. There should be an equivalent where, rather than doing blobology on a bicycle, I'm getting a flashing light that says, I know exactly where that bicycle is, and within the bounds of whatever privacy we want to set on it, I actually know which bicycle it is. Right now, we're still, anybody here drive with adaptive cruise control on a car? You ever go through a tunnel? I've done this in Boston, and it locks onto the wall of the tunnel instead of the car in front of you. That's blobology for you. Okay, it's okay because all it does is turn off when it gets confused, but we're moving into a world where we can't afford that kind of imprecision. Ditto with think about drones flying through the air. Kathy mentioned it. I'm a pilot. I'm not allowed to fly in instrument flight rules by the FAA without GPS plus a fully redundant ground-based navigation system. It's called the VOR system. We all pay for it with our tax dollars, and almost nobody really uses it anymore, but it is a fully capable ground-based backup for all that navigation that goes on. It's ridiculous to think that flying cars or drone delivery or any of that is going to be allowed to fly in our cities and our neighborhoods without similar kinds of ground-based systems. All these same technologies are going to be brought to bear on those kinds of futures. So again, I like this image a lot, particularly because it really captures the sense of the environment we've already built for ourselves is the greatest AI known to man. The built environment, and the current paradigm in robotics is doing a very poor job of making use of that intelligence. I hear robotics companies talk all the time about, oh, our mobile robot moves for a factory. It has no reliance on infrastructure. It's a bragging point. No reliance on infrastructure. Except for we need 4 walls and we need a white line going down the middle of the hallway and we need a great Wi-Fi network. And I think, how is that not infrastructure, right? We all rely on infrastructure all the time. That's how we move around. And there's no reason that robotics should be any different. Thank you.